Have you ever wondered why the sky is blue? Why is that the sun, which is actually white in color, looks yellow to us? Why does the sunlight usually look yellow to us? And why is it that the sunrise or the sunsets are usually red in color? Well, the short answer for this is because the molecules of our atmosphere, like the nitrogen molecules or the oxygen molecules, tend to scatter blue light more than red. So let's explore this in a little bit more detail. We've talked about scattering of light in previous videos. Basically, when light hits a tiny particle, it reflects light in all the direction, and that's what we call as scattering. And when this scattered light enters our eyes, we see that particle glowing the same color that it ends up scattering. So if it scatters, let's say, yellow light, then the particle will glow yellow to us. Now, the important thing is that the molecules of our atmosphere don't scatter all the colors of light equally. Now, to understand why that's a little complicated, because the physics of scattering is a little bit complicated, but in short, what's happening is that, you see, our white light is actually made up of 7 colors. Vibgyor, the 7 colors of the rainbow. And the reason we even see these different colors is actually because light is a wave, or at least it can be thought of as a wave, like a wave on a string. And then if we were to look at these waves, then it turns out that the shorter wavelength, when they hit our eyes, we perceive that as violet, and the longer wavelength, when they hit our eyes, we tend to perceive it as red. So as the wavelength becomes longer, the color changes from violet towards the red. And when we do the physics of scattering, it turns out that when we're dealing with particles of the atmosphere which are much smaller than the wavelength of light, they always tend to scatter the shorter wavelength more compared to the longer wavelength. Okay, we're not going to see why that happens. As I said, that's a little difficult. That's not little, that's actually pretty complicated. But it turns out that the shorter wavelength, which we see as violet, so this shorter wavelength, let's write that down somewhere over here. So this shorter wavelength scatters the most, and the longer red wavelength scatters the least. And therefore, if white light were to come and hit one of these atmospheric molecules, then they would tend to scatter blue light much more than the red light, because blue has a shorter wavelength, somewhere over here, compared to the red. Now, I'm pretty sure we might be wondering, why blue? Why not the violet itself? Because that has even shorter wavelength, isn't it? Well, turns out that the sun doesn't produce enough of violet in the first place. So there isn't much violet light in the incoming sunlight, and therefore there won't be much violet in the scattered light. Another reason why we don't see violet is because our eyes turn out to be not so sensitive to violet at all. So combined with these results, we don't tend to see violet, but we tend to see this indigo blue, which together we tend to usually call it as blue. So that's the blue light that gets scattered the most, and therefore the atmospheric molecules tend to glow blue in color when seen from any direction. And now we are ready to answer all our questions. So let's get rid of these pictures. First, let's look at what we would have seen if there wasn't an atmosphere. So let's say it's the daytime, that means the sun is right above us, something like afternoon. Then the rays of light would be coming straight down like this. Now, if we were to look in the direction of the sun, in this direction, then we would see the white sun. But if we were to look in any other direction, then there is no light coming towards us from any other direction, because all the light is just falling downwards. So we would see nothing. Therefore, all we would be seeing without an atmosphere is the white sun, and everything else would just look dark. And you know what? Let's perform an experiment side by side. All we would need is a flashlight, a tank of water, and some milk. When we add milk to this water, the milk particles are going to represent our atmosphere. So if you look at the flashlight directly without any milk particles in between, then all we see is the white light, and look at the sky, the whole thing has become dark, exactly like what we would see over here without an atmosphere. But now let's bring in the atmosphere. When we bring in the atmosphere, the sunlight strikes all these atmospheric particles, And like we discussed, they will end up scattering blue light the most. They do scatter all the other colors, but blue light gets scattered the most, and as a result, almost all these atmospheric particles will end up glowing blue. And so now, in whichever direction we look, all we would see is the blue light. And now in our experiment, if we bring the tank of water and start adding milk, the milk particles are going to mimic our atmosphere. Just like our atmospheric particles, they are scattering blue light the most. And as a result, the whole tank is glowing blue because everywhere the milk particles are mostly throwing blue light towards us. Beautiful, isn't it? But did you notice, as the sky became blue, the sun turned yellow? Why did it turn yellow? Well, if we come back over here, the initial incoming rays were white. But once it hit the atmospheric particles, they started scattering blue light. So from the incoming light, blue got scattered away. So if you look at the colors which are remaining now in this incoming light, violet was never there in the first place, not much. Indigo blue got scattered away. So now the incoming rays only contain green, yellow, orange, and red. Even these are being scattered, but not as much as blue. And so when we combine these colors together, we get that yellowish glow. And that's why the sunlight now, once it has entered the atmosphere, only retain that yellowish glow because most of the blue has been scattered away. And that's why when we look in the direction of the sun starts looking yellow to us. The same thing is happening in our experiment as well. Alright, finally, what happens during the sunset or the sunrise? Well, the effect or the concept is pretty much the same. The only difference now is that the sun is near the horizon. So let's say the sun is somewhere over here. Then the rays of sunlight, when it makes its way through the atmosphere reaching us, notice now it's passing through a much longer part of an atmosphere compared to before. And so by the time this light reaches our eyes, not only is the blue light being scattered away, but pretty much the green and yellow is also gone because it's hitting so many more atmospheric molecules. And so the only color that survives are the long wavelengths, which get scattered the least, that is orangish red. And therefore, by the time this light reaches us, it's going to look pretty much orangish red. And we can see the same thing in our experiment as well. If we look from the top, we can see the light is passing through the short part of the tank, only a short part of the atmosphere. So what we can do is we can take that tank and we can turn it so that we make that light pass through the larger part, the longer part of the tank. And so now if we see it from the front, notice the sun turns red, or at least reddish orange. Beautiful, isn't it? Also notice that the light that is reaching us is pretty dull. We can hardly see the flashlight now. And that's because most of the light has been scattered away from us. And that's what makes the sunrise and the sunset so beautiful, because we can see it directly without hurting our eyes. So to quickly summarize, the reason we see the blue sky and the red sunset is because when light or white light hits these atmospheric particles, they scatter blue light more compared to all the other colors. And one last thing I want to talk about before we wind up is why are the clouds white in color? What I mean is that clouds are made up of tiny drops of water. So when sunlight hits those drops of water, shouldn't they also scatter blue light in all the direction? That means shouldn't the clouds appear blue in color? Well, it turns out that only those particles whose size is smaller than the wavelength of light, only those particles can scatter blue light more compared to red, or shorter wavelengths more compared to the longer ones. And the oxygen, nitrogen molecules, or the molecules of the atmosphere, and the milk particles that we find in water pretty much fall under that category. But if the particles become much larger than the wavelength of light, in such cases, it turns out that they will scatter all the colors equally. And so drops of water are actually, which are found in clouds, are much larger than the wavelengths of light. And so when white light falls on them, they scatter all the colors equally. And as a result, they end up scattering just white light. And it's for that reason we will see We see clouds to be white. Even fog or mist also fall into that category. Even they appear pretty white to us.